when the percentage of the cold work is increased, we will see an increase in the yield strength also. Yeah? From when it is 0, it's about 150 megapascal, but when it is increased to when 60% of cold work is done, it can increase until 300 megapascal. Similarly, the tensile strength also increases, yeah, from 200 until about 400 megapascal when cold work is done, from 0% and 60% respectively. On the other hand, the ductility will decrease. So when no cold work is done, the ductility is as high as about 40%. But so it means the copper is easily deformable, easily formed, yeah, to different shape. But when cold work has been done, then it becomes harder and more difficult to shape. So this is, for example, before and after cold work. So after cold work, the diameter will decrease from 15.2 millimeter to 12.2 millimeter. So percentage of the cold work is expressed in terms of the percentage of the decrease in the area. Yeah, in this case, then pi r0 square minus pi rd square divided by the original area, pi r0 square. So 35.6% of area decrease. Okay. Then, as we have mentioned also in one of the slides earlier, that when we do heat treatment further, then we can make the material to weaken again. Yeah, so it means that the stress, the yield stress and the tensile stress can be made to decrease, while the elongation, while the ductility can be made to increase again. So this is an example of the result for polycrystalline iron when it is under heat treatment at 25 degrees Celsius, then minus 100 degrees Celsius, and further at 200 degrees Celsius, at minus 200 degrees Celsius, so cold temperature. The yield strength and the tensile strength will decrease with increasing test temperature. Yeah, so here, when temperature increase to 100 degrees, to minus 100 degrees, and then to 25 degrees Celsius, we see here that the yield strength decreases also, from here 600, 700 megapascal decrease to 300 megapascal, and then here further to 150 megapascal. Similarly, the tensile strength decrease from around 750 megapascal here to 400 megapascal, and this one to about 300 megapascal. Why is that? So the vacancies help dislocation to move past the obstacles. So when the temperature is increased, then more vacancies are created, because of the phonon, of this increased temperature, because the atoms can move more easily and vacancy can occur. And this will help dislocation to move past the obstacle caused by the entanglement between the dislocation. This. So we have here displacement, dislocation is trapped by an obstacle, but upon heat treatment at increased temperature, the vacancies will replace the atoms on the dislocation half plane. So then the dislocation can glide. So this dislocation from here move upward, because of the occurrence of vacancies. Then dislocation at this upper part can pass the obstacle easily. So this shows the effect of heating after percentage cold work, what we call as annealing process. Annealing process. 1 hour treatment at T annealing decreases the tensile strength and increases the elongation or the ductility, percentage elimination of ductility. So in this case, we can reverse the effects of Coldwork. Because when for example, the metal is too strong, we cannot form it at all. We cannot make it into various shape or form. What should we do? We should do annealing to decrease the temperature, the tensile strength, and increases the ductility. So here, when we anneal the temperature at higher temperature, ductility, shown by this red line, will increase. Oppositely, on the other hand, the tensile strength will decrease when we do annealing. So the blue region is called as the recovery when we do annealing, and then at this orange region, the material will be having recrystallization. Recrystallization will occur, and then it will further grow the grain again, the crystal again at higher temperature. So annihilation reduces the dislocation density due to diffusion. We have here in the extra half plane of the atoms, the other one extra half plane of the atoms. Atoms could diffuse to the region of tension here. So dislocation will annihilate in the middle, and form a perfect atomic plane because of the diffusion of the atom due to the thermal annealing. So scenario 2, in scenario 2, the dislocation is blocked by an obstacle. It cannot move to the right, this dislocation. The gray atoms leave due to the vacancy diffusion because of the thermal annealing. Vacancies occurs. Then the dislocation can climb to the upper plane of the crystalline structure. The climb dislocation then can now move onto the new slip plane and pass the obstacle dislocation. And then here, opposite dislocation from the upper plane can meet at this region and then annihilate. So this process is called as recrystallization occurring at high temperature. So new grains are formed, new grains will form, and it will have a smaller dislocation density. So this is the opposite effect of Coldwork. The new grains that are formed will have smaller size than the initial Coldwork ones, and it will consume the Coldwork grains. So for example here, initially after Coldwork, the shape, the crystalline shape, after 33% of Coldwork in brass, an alloy of zinc and copper, if I'm not mistaken. Then you put this under anneal temperature, high temperature, at 580 degrees. After 3 seconds, we will start to see that new crystal will nucleate. New crystal will form in some regions. Then after 4 seconds, the nuclei, remember that nuclei are the origin of crystal grain. More nuclei will form like this. And after 8 seconds, all nuclei, all the new nuclei will consume all the remaining region, and they will start, when you then increase the temperature, then they will start to grow. Nuclei and nuclei combine to each other and grow into larger grain. At longer time, the larger grain consumes the smaller one. Why? The grain boundary area and therefore the energy. So here, after 8 seconds, from this picture, after 15 minutes at 580 degrees Celsius, then larger grain will be formed. So the empirical relationship is given here. The diameter, dn of the grain diameter at time t, this is the initial diameter, then equals to the coefficient of the dependence on material and temperature and times the elapsed time. You have to show the relationship between the change of the grain diameter. This process is called as the Oswald crimping. So TR here is recrystallization temperature. So after you increase temperature to this high temperature, ductility increases, new crystals form, and then it goes into larger grain size. Okay. So for example, here, this is the Coldwork and recovered grains. It has long oriented larger grain. When you anneal in high temperature, new grain will form, and then after you anneal further at higher temperature, these grains will grow, yeah, to larger size. Let's give some example of Coldwork calculation. A cylindrical rod of brass originally is 10.2 millimeter in diameter or 0.4 inch is to be Coldwork by drawing. The circular cross section will be maintained during the formation. A Coldwork tensile stress in excess of 55,000 psi or 380 megapascal and ductility of at least 15% elongation are desired. Furthermore, the final diameter must be 0.3 inch or 7.6 millimeter. Explain how this may be accomplished. If we directly draw the final diameter, what happens? From 0.4 inch to 0.3 inch. So the percentage Coldwork is A0 minus AF divided by A0 times 100, 1 minus AF divided by A0 times 100. AF can be calculated from the pi times the diameter divided by 4. Okay. Here we need to do 43.8% of Coldwork, right? From 0.4 inch to 0.3 inch. However, from the graph, 43.8%, this part here. Yeah, then the yield strength will be 420 megapascal. The required one is 380 megapascal. So this is still too strong. Okay. Sigma y, the yield strength is 420 megapascal. Tensile strength is 540 megapascal, which is still larger than what we want, which is 380 megapascal. What should we do? We can do? Annealing. Okay. The percent elongation is 6% at this 43.8% Coldwork. 6%, while the desired ductility is 15, at least 15%. So, or better, more. What to do then? We should do then temperature annealing. What can we do? Yeah, what we do is the tensile strength should be larger than 380 megapascal. Yeah. So it means the percentage Coldwork should be larger than 12%. Larger than 12%. The previous one is 43.8% is too large. Percent elongation should be smaller than 15%. So the Coldwork that has to be done should be the ductility should be smaller than 27%. So the working range is limited from of Coldwork is 12 to 20%. What we can do is we can do recrystallization. We could cold draw and then do annealing to increase the ductility again, and then doing cold draw again to strengthen again the material. So we need a Coldwork between 12 to 25%. Let's say we use percentage Coldwork of 20. The diameter after the first cold draw before the second draw can be calculated like this. Okay. So the second diameter, if it is 20%, will be 0.335 meter when we do 20% cold work. While the shape of the diameter is 0.3 inch, yeah, must be 0.3 or 7.6 millimeter. But now if we do 20% cold work, we will obtain 0.335 meter. So summary from cold work 0.40 inch to the first cold work to 0.335 meter, the percentage cold work is 30. A nail above, yeah, D02, and then after that we do another cold work to make the diameter from 0.335 meter to 0.3 meter. So the percentage of the second cold work is also 20%. So we do 2 times cold work, 30% and 20%, and in between we anneal the temperature. We put the material in high temperature treatment. So eventually we meet the requirement. The yield strength is 340 megapascal, which is still lower than 380 megapascal. Tensile strength is 400 megapascal, higher than 380 megapascal. The ductility is 24%, which is larger than the required 15% ductility. So rate of crystallization can be, so from here we know that that is why that in actual steel processing or metal processing, sometimes we have to repeat this between these two, cold work, annealing, cold work, annealing. If we do only cold work, we strengthen the material, but maybe we will lose ductility, which will make the material very hard to make, to form. So then you need to do annealing to increase the temperature to allow recrystallization to occur and make it more ductile. After that, you do secondary cold work to strengthen the material again. So the rate of crystallization when we increase the temperature, or we call it hot work, log R can be calculated using this formula. Log R, the rate, equal to minus log T equals log R0 minus E divided by KT. The log T equals, or log T here equals to C plus B over T, while R equals to 1 over T. T here is the temperature. So the hot work is when the temperature is done above the TR, the temperature of recrystallization. Cold work is when the process is done below the recrystallization temperature. When we have smaller grains, it will be stronger at low temperature, but it will be weaker at high temperature. The recrystallization temperature is usually 0.3 of the melting temperature to 0.7 of the melting temperature, the range. Recrystallization temperature depends also on the percentage of the cold work. It will decrease, with increasing cold work. So a summary of this chapter, dislocations are observed primarily in metals and alloy. The strength is increased by making dislocation motion difficult. So by putting barrier to prevent the defect to move, to be able to move. Because basically deformation occurs when the dislocation can move. Dislocation move to the edge, where it will create an extra crystal plane, which we see externally from external point of view as deformation. To increase the strength, to make the dislocation motion difficult to happen by decreasing the grain size, where we will increase the barrier between the grain, which means that it will create boundary, the boundary create barrier for the dislocation to move, or by solid solution strengthening, introducing impurity, which can block or precipitation, impurity or precipitation, impurity, yeah, which will block the dislocation or will create a more balanced energy for such that the dislocation cannot be in motion. Then by precipitate strengthening, where we introduce different type of material into the structure of the metal crystal. And finally, by doing cold work, when we increase the density of the dislocation such that they will entangle to each other and then make them to be more difficult to move. But sometimes we want to process again, we want to shape again the device, the material, which cannot be done if the tensile strength or the yield stress is too high, because then we cannot make a plastic deformation. What can we do is we can do heating or annealing to reduce the dislocation density, doing again recrystallization and increase the grain size, which will decrease the strength but increase the ductility, so that then it will be more formable. Okay, so that will be all for this chapter. Are there any questions so far regarding dislocation motion, the strengthening mechanism, and processing?
Yes, sir. Actually, I have a few questions about that. So, for the sleep system, I want to ask about how can we know the lambda and psi value? Is it like the standard value for each metal? So,
Yeah, the lambda and phi, if we have a metal crystal, we have to put under XRD, yeah, so that we know the crystal plane. Okay, so if we know the crystal plane of the, let's see here, we have a material like this. So from this particular system, we know, yeah, what plane they can have, what slip plane they have, right? For example, like for FCC, the slip plane is in the family of 111. Slip direction is in the family of 110. Okay, so if for particular sample root bar, yeah, it depends. Yeah, the lambda and the phi could be horizontal like this, could also be, for example, vertical, or could also be making an angle. How do we know then? We can uh, we can put this material, for example, under X-ray. This is for single crystal, yeah. What I mean is doing for single crystal, monocrystalline material. You can put under X-ray to know the orientation of, let's say, for example, the top part of that. What is the plane here? What is the plane in this region? Is it 110, 111? From there, then you can know what will be then the orientate how many degrees of this 111, for example. Okay, so let's say, for example, if we draw it in within the crystal lattice, the 100 plane is this part, right? This is the 100 plane. Okay, so the 111 plane will be in, let's say, for example, this part, and then this is 111 plane. Okay, let's say, for example, that based on the XRD, we know that this part, the end of that material is 11100 plane. Here is 100 plane. Then from there we can calculate, right? This is the A, and this is the end of the crystal plane, the slip plane. So from here we can calculate the angle here. This becomes the phi. Okay, while the lambda depends on the stress that you put. And for example, if you put the stress also within this the F, yeah, the F, the sigma axial. So it means your shear stress will be in this direction, right? This is the sigma R, the shear residual stress, right? So in that case, in this case, the lambda will be the same as the phi. But you could also, for example, apply this kind of stress, right, to this thing. So then the angle of lambda will be different than phi. So the lambda is the angle between the direction of the sigma, the stress, and the direction of the resolved shear stress. Resolved shear stress is, in this case, this parallel to the direction of the slip plane. In the case of FCC, it will be 111 plane. While that is the lambda, yeah? While the phi depends on the plane of the area of that whole material, okay, where you apply the sigma. Yeah, in this case, uh, if this happens to be 100 and the slip plane is 111, then you can calculate the plane between 100 and 111 plane. Okay, so how do we know that it is 100 in the edge of that material? Yeah, we know that we can know that using XRD, X-ray diffraction. Is it clear?
Okay. Okay, sir. So, um, kalau so we have to know the plane first from XRD, and then um, the force that is used, the direction force that is used, gitu ya. Baru bisa kebentuk dislocation, tergantung
Yeah.
dengan direction force-nya, gitu ya.
Yes. So we see, let's say, look at the slide again. Slip plane. Ah. So here, each material has particular slip plane, right? So copper, aluminum, nickel, silver, gold, 111. 111 is a slip plane. So now we need to know the for example, we have a bar, a road bar like this, copper. What is the material here? The plane here. So if this is 111 also, then that is the slip plane. So then if it is 111, what will be then the lambda, the phi? What do you think, Ezra? If this is 111 on the end, on the top and the bottom end, or the horizontal plane is 111, what will be the phi then?
45 degree.
No,
One.
the phi will be 0 degree. So it means then the slip plane is located parallel to this plane, right? If it is parallel, then phi is angle between the axial plane and the parallel, right? Here. And here, wait. Here, the phi here is the angle between the area of the upper part here where the axial stress is occurring and the angle to the angle of the slip plane. Okay, so if this 111, if this area is 111, so for copper, the slip plane is also 111. So phi is 0 degree, right? Because it is the same. Understand?
Oh, yes, sir.
Not understand. Okay, right? The same. What if, for example, on the other hand, you see if we have aluminum, alpha iron, for example, or molybdenum, let's say molybdenum. Okay, the upper plane here is, let's say, the upper plane is 100 also. What will be the phi then? Alpha iron. If the upper part, yeah, the end part of the road bar is 100, what will be the phi?
Okay, 100 is like datar gitu kan, and 110 is like wait, one
Ayo,
one
what is the
one
phi?
zero.